In this lab, we are going to talk about optimization in ANSYS. So this is the content of the lab. I'll show you the general design process tree that engineers follow, and then followed by the optimization of the talk arm, and then there is one assignment for you. Let's talk about the design process. So whenever an engineer wants to design an object or a product, first of all, they set up the initial design with some constraints and dimensions. And while setting up the initial design, we do not know about the exact shape or stresses that are being produced inside the product. The next step is to follow is to conduct the simulations in ANSYS, and after conducting the simulation based on applying the boundary condition, we evaluate the performance of the product. Performance could be the study of deformation or equivalent stresses, or maybe the natural frequencies of the object, or it could be anything related to transient analysis or thermal analysis. So after evaluating the performance, we need to check whether the performance is being satisfied or not. Let's say we need to look at the safety factor of a product that we are designing, and if the safety factor is less than 1 or maybe 1.3 or 2, the whatever goal we specify, and after analysis, if the safety factor is less than the goal that we specified, we will say that our design is not satisfied and we need to improve our design. And what is meant by improving the design, it could be related to updating the forces that are acting on the object, or it could be related to the shape of the product that we are designing, or any other geometric properties, or maybe the material. So we reconduct the simulation, evaluate the performance again until the desired results are achieved, desired goal is achieved, and after that, if the goals are achieved, we say, okay, this design is finalized. So this is the general design process that we usually follow. So this can be set up in ANSYS workbench using different schemes that are available. So in general, there are few key terms that we need to look at. The first one is the design variables. So the design variables are the variables that we select to change during the design process. So let's say we want to design a beam, and we select its thickness as a design variable. When we select its thickness as design variable, we can change the thickness of the beam from let's say 5 millimeter to 20 millimeter with a step of 1 millimeter, and evaluate our performance of the beam. And then after that, we select the thickness that gives us the satisfactory result. So the second key term in the design process is the design space. So this is a space that is spanned by the design variables. So when I say if we have only one variable, it will be a set of linearly spaced points. So a line will be the design space. If there are two variables, then the design space will be then the design space will be a surface, a plane actually. And then if there are three design variables, then design space will be a full 3D cube. Finally, we have design points. So any point that lies in the design space is called a design point, and this design point is used to evaluate the performance within the design space. So let's say Let's talk about the thickness example again. And if a beam has a thickness, if a beam has initial thickness of 5 millimeter and we want to change it to 10 millimeter, there are infinite many number of points that we can create between 5 and 10. So we may need to limit our design points to 3 or 4 so that we can have less computation while performing the optimization process. So let's look at the design of a torque arm. Here we have the initial dimensions of the torque arm, and it is 5 millimeter thick. The material used is 200 gigapascal and a Poisson ratio of 0.3 is used. We need to first of all determine the deformation and von Mises stress for this initial design that we have, and then we need to optimize the dimensions of this you can say slot so that the minimum safety factor is 1.3. So this is the design problem that we need to solve. Let's shift to ANSYS and solve the problem. Let's start with modeling the geometry in Design Modular. After opening the Design Modular, the first step is to change the dimensions to millimeters to centimeters and then go to XY plane. And after that, I'll draw two circles, one at the origin and the second one on the x-axis. Let's dimension these circles. So dimension of first one is 8 centimeter and second one is 4 centimeter. And they are separated by a distance of 36 centimeters. Let's draw the center arcs. Make sure that they are concentric with the previous circles. However, do not apply any other constraints on that. Like if they are connected to y-axis, so we need to remove those constraints. So we need these arcs to be free, and then we need to draw the lines connecting these two arcs. After that, we can make these lines tangent to the arcs, but first let's dimension the arcs that we just created. So the dimension of the first arc is 6 centimeter and then the other is 4 centimeter. Let's apply the constraints. So these arcs are tangent to the lines. So we have this basic shape of the torque arm. Let's draw the slot using the oval sketch that we have. So first we need to specify the radius, which is 1.5 centimeter. I did that previously, and now we need to add the distance between the circles, which is 4 centimeters from both ends. So this way we can define the torque arm completely, and we can convert this torque arm to a 2D sketch using the tools command and using the concept, and we can use surface from sketches, apply and generate. Let's move on to model for further analysis. After modeling the geometry, I'm going to change the analysis type to 2D before opening the model so that I can analyze the torque range in 2 dimensions since its thickness is very small as compared to its length. Let's open the model. After opening the model, I can see that this is a 2D problem, 2D plane stress problem, and the thickness of this rod torque arm is 5 millimeter. Let's generate the mesh. let me change the relevance to 100 and let's generate a fine mesh for this one. After generating the mesh, I'm going to assign fixed support at left edge here and then apply a force of 5000 Newton in x direction and 5000 Newton in x direction and the force of 400 Newton in y direction. So this is the force that will act on the second hole of the torque arm. We need to find the maximum equivalent stress base safety factor, the value of the stress, value of deformation, and finally, I need to look at a safety factor based on fatigue. So we are analyzing this under the Soderbergh criteria. So mean stress theory is Soderbergh criteria that I'm going to use. This is a conservative one. And stress life method is used with fully reversed loading cycles in this case. I'm just going to solve this problem. Okay, after solving, we can see that the minimum safety factor is 4.65, which is at inside of the slot in case of static loading. The maximum stress is also at that point, which is 53 megapascal, and the deformation is zero point 0.1 millimeter. Finally, we have a safety factor which is 1.6, and it acts at and it is at the same point, at the point of maximum stress. I can refine the mesh to see if to check if the safety factor depends on the meshing or not. So the first step is to insert the sizing here. So by default, the sizing is set to 11 millimeter. I'm going to change this to 5 millimeter, which is half of the case, and rerun the mesh settings. So the mesh is refined. Let's look at the problem. Now the safety factor is at about 1.55. Let's further refine the mesh a bit. Okay, the safety factor is at 1.48 and it is converging, it is still converging, and the stress is increased from, so the stress is about 58 megapascals. So I think this mesh is quite good and we don't need to further refine this. Let's move on to the optimization part. For now, we see that we have a safety factor of 1.48 under fatigue loading. And if you look at the results here, you will see this checkbox. And whenever you click on this checkbox, you will see a small p that will appear in the checkbox. I move to the main project window. There we see we have this parameter set now, which is appeared at the bottom of the workbench tree. So it has only one arrow. This shows that we have parameters that are from the output tab. Similarly, we can add multiple parameters here, like the thickness can be changed. Apart from that, we can look at the geometry of the, we can look at geometric properties like the mass and volume, and we can parameterize these as well. the forces, the applied boundary conditions can be parameterized, and all of the results can be parameterized. So for now, I'm looking at the single objective, which is the fatigue safety factor. And I want to change the dimension of this slot so that the safety factor is about 1.3. So I'll go again to the geometry and select the required dimension that I want to change. Here in the sketching, I can see that by changing this radius, I can change the thickness of this slot. So let's parameterize this radius, which is 1.5 centimeter R6. And let me change this to thickness. Let's say this parameter name is thickness. So we have R6 in the parameter tab, and when I close the geometry, you will see a parameter set is generated. I can click on this parameter set, and here you can see there are two parameters that appear. The first one is safety factor, which is currently 1.484 millimeter 484, and the thickness uh, P2 is 1.5 centimeter, which is the thickness of the slot that we want to change. And in the design parameters, we can manually add multiple points and check whether the results are obtained or not. Another way to solve this problem is to use the optimization tab. If I go to design exploration, you can see we have the direct optimization under design exploration, and I can insert this direct optimization under parameter set. Now, after defining a parameter set or setting it like this, we can move on to the direct optimization tab. Here you can see that we have multiple steps in which we can select the optimization technique, define our objectives and constraints, and finally specify the lower and upper bound for the input parameter, and then any parametric relationships that we want to add, and then we will have the results. So first of all, let's look at the optimization methods that are available. So the first method is screening. And whenever you select a method, its details, general overview will appear here in this optimization schematic. And the screening method is usually uh, used for the preliminary design, and if you have multiple objectives or constraints, it supports that as well. It can be used for, you can say, all type of input parameters, whether they are manufacturable inputs or they are continuous variables. So for now, the current setting is we will have 100 samples and find 3 candidates. If I change this to 4, this will be updated to 4 candidates. So out of 100 samples that were generated, this algorithm will give us the top 3 candidates based on our objectives and constraints. The second method is MOGA, which is multi-objective genetic algorithm, and as the name suggests, it is used for multiple objectives and used for finding the global optimum. So there are methods that can result in local optimum, and there are methods that can result in global optimum. So this MOGA is perfect for global optimization. And currently the settings are set to 100 samples that were generated initially. Then for each sample, 50 more samples per iteration were generated, and then as a result we will have 3 candidates in maximum of 20 iterations. So this is the general setup, and these are the input parameters that can be changed. The next is nonlinear programming by quadratic Lagrangian. It is a gradient based method, and it can be only used to optimize a single output parameter with multiple constraints, and it is limited to the input parameters that are continuous. So we cannot use this NLPQL for discrete input parameters. Here we have this mixed integer sequential quadratic programming method, and you can see the details. This is integer have a smooth influence on the model function. That function do not change drastically when in or decrementing an integer variable. So successive quadratic approximations are applied in this case to get the optimized results, and it uses the forward difference method for finding the optimized solution. Then we have adaptive multi-objective algorithm, which is the variant of a genetic algorithm too. It also supports multi-objective and constraints and finding the global minimum. However, it is limited to continuous and manufacturable inputs only. So these are the two types that it supports. And finally, we have adaptive single objective, which is limited to optimizing the problem for single objectives only. So I'll use a screening method, which is the initial optimization method here, and will generate 10 samples only. So the objectives and constraints in my case is I want to find the safety factor so that it is 1.3, and let's apply some constraints on objectives. So the minimum safety factor cannot be less than 1.1. So finally, we have the variable space. So this is the design space bound on the design space, and I want this thickness to change from, let's say, 1 centimeter to 2.5 centimeter, and allowed values could be any means that this could be a continuous function. Manufacturable values, when we click on this, we have to specify the multiple levels in which the product can be manufactured. So in this case, I'm going with the allowed values, that is a continuous function. And after setting all of these parameters for different schemes, you can click on this update button until the results are acquired. So after clicking on update button, ANSYS will generate the design space based on the settings and will solve the problem for each of this design space automatically, and then recommend the top 2 or 3 candidates based on the settings. Let's wait until all of the solutions are run and we get the results. After the analysis completed, let's look at the raw optimization data. Here we have a list of thicknesses and safety factors that are produced, and based on this we can have a look at the candidate points that ANSYS suggested. So for thickness 1.975 centimeter, we have a safety factor of 1.26. For candidate point 2, 1.825, and we have a safety factor of 1.33. So we can use any of these as uh, they fall within our constraints. Let's look at this trade-off here, and you can see the feasible points. As we decrease the thickness, how the safety factor is increasing. So decreasing the thickness means here we are increasing the material, or we are increasing the material in our case. So this is actually the cavity thickness. So the result is as expected, and if we look at sensitivities, we have this negative sensitivity, meaning that if one factor is increasing, the other is decreasing. So there is a negative correlation between these two. Here you can see the history of the analysis and optimization results. So these are our constraints that we have added. So this is the objective value, which is 1.3, and this is the load constraint. And you can see the ANSYS suggested the points that are here. So this is 1.33. This actually falls within the desired space, 1.2689, 1.19, and these are. So here we have the three candidate points. Now, if I want the geometry to be updated based on this candidate point, I can click here, right click here on any candidate point and select insert as a design point. After inserting the candidate point as a design point, you see this is set as DP1. I can move back to this parameter set, open this, and you see that the DP1 is inserted here. And now after clicking on this DP1, I can select copy input to current. So the current design point is set to DP0, and I can evaluate this DP0 again. You will see that the geometry will automatically be updated based on this settings that we just selected. So let's wait until the solution is done. When the design point is updated, I can see the thicknesses here and the safety factor. I can move back to the geometry in the design tree and open this. Here, when I look at the thickness, you see that this geometry is updated based on the optimization results, based on the candidate point that we selected. So the radius is now, or the thickness is set to 1.975 centimeter, and this geometry is the updated one. Let's close this. So there are other design exploration tools that you can explore on your own. So the most useful are response surface and response surface optimization tools as well. You can look at the details in the ANSYS guide whenever required in future. So that's all about this optimization in ANSYS Workbench. And let's move on to the assignment part. So this is the assignment that you can solve on your own. Here, the dimensions of the holes are fixed. So they are like 120 millimeter apart, and these two holes are 200 millimeter apart. So here you need to decide the dimension of this triangle, so that the factor of safety is 3 for the design, and you can use any topology that you can want. So this is the optimization problem, and you may need to parameterize one or two parameters together, or maybe one parameter which is linked to the other two parameters as well. So it's up to you how you solve. Thank you so much for your time, and I'll be back with the next lab soon.